Hello and welcome to today's webinar presented by Delubal Software. Today we'll be working in our structural analysis and design software, Rfem. The topic for today's presentation is Tekla Structures integration in Rfem 6. My name is Amy Heilig. I'll be your moderator, answering any questions you may have. I'm the CEO of the US office and also a technical support and sales engineer, and I'm located in Philadelphia. My colleague, Alex Bacon, will be your presenter. He's a technical support engineer, also located in our Philadelphia office. And lastly, we have Siska Choa, who will also be a moderator, answer any questions you may have. She's a technical support engineer located in the Philadelphia office. If you have any questions about today's presentation, we encourage you to go ahead and send those into the dialog box here. If by chance we don't get to all your questions, we will certainly send you a follow-up email afterwards. As far as the content over the next hour today, we do want to begin with a brief introduction to the Tekla Structures interface, as well as the Rfem 6 integration options. We'll spend some time there before moving on to our first example. For this, we'll begin in Tekla Structures, where we will export the model out to the FEA program Rfem 6. So once in Rfem, we'll take a look at the model. We will design a few members and optimize them. After those changes are made, we'll take that updated model and export back out to Tekla. And with that said, I'll go ahead and turn it over to Alex.
Great, thank you, Amy. So I will begin with giving some general information on the Tekla Rfem 6 interface. So currently, the interface supports Tekla versions 2021 to 2024. This interface is a direct one between Tekla and Rfem, and so the two programs need to be installed on one single PC. Then you want to make sure in your Rfem 6 program and option settings that the web services is checked on here, so that every time Rfem 6 starts up, it will start up the web services. And this should be on by default, but it's always good to check that. And then the plugin also must be manually installed after installing Rfem 6. So you can find that setup file under this pathway after you install Rfem 6, and then once you install that, then you should be good to go. The structural objects that can be transferred between Tekla and Rfem 6 include members and surfaces, sections and materials, supports and hinges, along with rigid links. Here are the export options. So if you are exporting from Tekla to Rfem, these are the export options you will get. So the first option you can see here is the physical model option. And this is basically like a CAD model. And so it's the solids without any consideration of the axial positions. And you can see here with this would be a physical model. And if you would export this physical model, you can see that the axial positions here are not lined up or connected at all. And the wall here is basically just framing into the bottom of the slab. And so there's going to be a space there. And so if you export this physical model, this is what you're going to see in Rfem, which isn't good. And so what you need is an analytical model to be created. And you can see here that the axial lines of each element are connected correctly. And so then you will get that correct analytical model in Rfem 6, which is needed to run the structural analysis. So that would be the second option here. Analytical model is what you'd want to choose if you're looking to run a structural analysis. Next, you have this option for exporting rigid links, which is checked on by default. So if any rigid links are defined in Tekla in the analytical model, then those will be exported into Rfem as well. This option for creating a unique profile for each set of members, this is checked off by default. If you check this on, then the cross-sections, the same cross-sections are going to be given separate index numbers. By default in Rfem, a similar cross-section is summarized with only one index number. And so you will get unique index numbers for similar cross sections if you check this on. Next option is setting the global z-axis. By default, this is set to upward in Rfem, but if you uncheck this, it'll be set to downward. And then lastly, these options if you want to create a new model in Rfem when you export, or you can overwrite the current model that's open in Rfem. Then we have our import options. So here we have a couple import types. This is when you're going from Rfem to Tekla. So you can overwrite an existing model, you can append an existing model, or update an existing model. Overwrite means it'll completely wipe the file and everything will be started from new when importing in. Appending is more for adding if you're looking to add some additional members or parts to the model. And then update should be used if you're looking to update things like materials, cross sections, and then it can also do new objects as well. And then here's some mirroring options if you're using the overwrite or append option. And so you can choose to mirror about the X, Y, or Z coordinates with that option. Next is the conversion tables. The conversion tables are used for mapping the cross sections and materials between Rfem and Tekla. This is required since the names of materials and sections between the two programs are not completely the same. And so these conversion mappings are needed. And this table is what's used in Tekla to enter those conversion mappings. And so the left-hand side column here controls the conversions for exporting from Tekla to Rfem. This right-hand column controls the conversions for importing from Rfem to Tekla. Then each of these columns is further subdivided by section and material, and then further subdivided by if this is a regular expression or if it's not a regular expression. And regular expressions allow you to convert multiple objects via only one entry. And so I would like to show you, we have some documentation on our website regarding regular expressions. If you're not sure how to create regular expressions, this FAQ, which is implanted in the PDF, which you can download anytime during this webinar. And so a regular expression is basically allows you to convert a whole series of sections with just one expression. So down here is a normal conversion. So you have the IP 120, name in Tekla, and then the name in Rfem 6 here. And so that's mapped out, but it's only that one section. And so if you wanted to have just all of the series of IPEs, for example, mapped out in one expression, you can do that with a regular expression. And so with that, you would take the 120, for example, or any number here and use this expression to map that out or to be able to enter in any number in Tekla. And then that is linked with this number 1 here index for the Rfem 6 name. And so then that allows you to enter any number in and have that conversion work out. And then you can see down here in the conversion table, this is what entering that expression would look like. So on the left-hand side here, you have the Tekla name. On the right-hand side, you have the Dlubo or Rfem 6 name. And so you would create a new expression. And when creating a new expression, you choose if it's a regular expression, if it is a import or an export conversion, and then you can choose if it's a section or material with that dropdown. And so that is how the conversion tables work. Next, I would just like to go through a couple examples of possible workflows between Rfem and Tekla using this interface. So the first possible workflow is to take the analytical model in Tekla and export that into Rfem. So information about sections, materials, supports, etc. will be exported into Rfem. Then in Rfem, you can add some loads and run an analysis and do some design and optimization. And then any sections or materials or new objects that are added or changed in Rfem can be updated back into the Tekla model. The second possible workflow is pretty similar to the last one. Basically, you can take just a simple or just a part of a Tekla model and export that into Rfem and do your modifications and design work and optimization, and then update that back into the Tekla model. So you can see here just part of it. This is what we will be doing today for our example. And then the third possible workflow is taking a structural analysis model from Rfem that you've modeled and created with some loads and design and optimization, and then that can be imported. The complete model can be imported to Tekla or only part of it, and then you can continuously update that Tekla model as you make changes such as sections and materials and etc. And so now that's all I have to say for the presentation portion. And so now I'm going to open Tekla. And so up here in the ribbon, you can see we have the Doable tab. And under the Doable tab, we have our buttons here for exporting and importing into Rfem, and along with the conversion tables. So with the conversion tables here, you can see I have my materials and sections defined for exporting to Rfem. I would like to say that with these conversion tables, once you create these conversions, you can use them for all future projects. And we may even have some in here that some common materials and sections in here defined. So you may not have to define all materials and sections. And with that said, so I want to now export this model into Rfem. So I'm going to move the window over, and you can see here I have a blank model of Rfem opened up. And so now if we export to Rfem the physical model, we can see what that looks like. And so the connection between the two programs is going to be made. And then once that's made, you can see the status in the bottom left-hand corner of Rfem. Will show that the data is being transferred. And now we can see our model in Rfem. And I'm going to turn off the numbering and also the axes and the grid. And so if we zoom in here, you can see that it looks like our members are connected. So it looks like our beams are connected to our columns. And if we go into Tekla, we can see that that is also the case. But in Rfem, if we change our model from a rendered view to a wireframe view or an analytical view, you can see that those members are not actually connected in the wireframe. And so what we need to do to fix this is in Tekla, we need to create what is called an analytical model. And so to do this, we can go up here to the analysis and design, and we can open up the analysis and design window here. And this is where we can create a new model. So we will click on create new, and this will open up another window with some basic properties to define. So in this dropdown, these are just some old Rfem 5 presets that we don't need to pay any attention to, so we want to set those to blank. And then for the name, we will give it steel, because we're only going to focus on the steel portion of this model. It is possible to export the concrete surfaces as well, but we are just going to focus on the steel for now. You can also then define some more settings here, and once you have those defined, you can save them as a preset. You can see here that I have a preset defined, and so I can choose that and click load. And so now all of my settings here from that preset have been loaded in, and so then you don't have to define these every time. And so now I'll click OK, and we have our analytical model created there. And now what we need to do is select all of our steel members to be imported into, or to be taken into consideration as the analytical model. And one thing I would like to note is if you have any connections here or any steel connections, you can have those not be selected because we don't want to create analytical models based on any of the steel components or steel connection components that are defined in Tekla, because then those are just profiles and they won't transfer over to Rfem correctly. So you can turn this button here off, and so you won't select those components when selecting the model that you would like to convert into an analytical one. So once you select those members, we can click Add Selected Objects. And so now we have our members here. You can see we have our analytical members created. And these are generated based on the axes of the beams and the columns. So that is how they reference the center of the beams and columns. And I can double click on one of these to show you those properties. So you can see here this beam is defined as a beam with some start and end releases. You can see by default these are pin connections on all of these. So what we want to do, and you can change this setting in the future so they are rigid connections, but for now I'm going to highlight the whole model and I'm going to double click on one of these beams, and we want to change that connection to a rigid connection. So we'll choose connected, rigid connection. We want to choose connected again, and we want to choose our rigid connection. We want to make sure this is set to connected and not supported because we're changing the connections and not supports. And so once that is selected, we actually want to re-highlight the model here and click Modify. And so now all of our connections are set to rigid. Doing that though, changed our columns, our classification of our columns. So let's double click on one of our columns. We want to change that back to column, and we can highlight our columns here, change those back to column, modify, and click OK. So now all of our connections here should be rigid. So now we want to define some of our beams as trusses. So let's double click on one of our beams here, and we want to change the classification or the class here to beam truss. So then when these are imported into Rfem, these truss members, or the members here, will be set to the member type truss. So they will have pin connections at the end. And so now that we changed that, we want to select all of the members that we have that we want to change to truss members. So once we highlight them, we can choose Modify and click OK. And so now you can see when I zoom in here, those beams are green now, telling me that they are truss members. And we also next want to define some supports. So we want to give our columns some supports, and we can do this in Tekla. So we can double click on one of our columns here, and then we can go to the Start Releases and End Releases tabs. You can see that the start releases are defined as yellow, or color coordinated as yellow, and then the end releases are purple. So you can see the purple node here and the yellow node. We want to define this support at the yellow node, and so then we'll change this to supported. And you can see there's some predefined supports here. I want to choose the hinge support. And you can see the degrees of freedom here. I want to fix the rotation about the z-axis. And so now that we have that support defined for the start there, we can highlight our columns and choose Modify and click OK. And now the supports are added at the bottom of our columns. You can also double click on the node here and you can edit the support of the node as well if you'd like. Next, also one thing to mention is it is useful. You can define some presets as well for these. So if you create a support, you can name it and save it as a preset. Next, we want to add some supports to our steel members here that are framing into our concrete model portion here. So we'll double click on those, and you can see here that we want to edit this end purple node. And so we want to make this a hinge support with a, well, it's going to be a roller in the X hinge support. So we want to free up the translation in the X direction and fix the rotation about the Z. And again, you could save this as a roller and X support. Click Save As, and then that will be entered there. And so we want to apply this support to all of our members here. And choose Modify. Click OK, and now you can see those supports are added to the end of our members there. And so yeah, now we have our supports created. We want to check all of our connections. And so to do this, we can open up the Analysis and Design Models window and go to the Display Warnings. And you can see we have some warnings here. This first warning we can ignore, but the second warning about a member being shorter than the minimum length we want to check out. So if we want to see exactly what that means, we can click on Details. And under Details, we can go under that warning and we can see and click on the analytical part that warning has to do with. And so then we can see that's highlighted graphically here. And so then we can right click, and if we still aren't able to locate that warning, we can go to Zoom and Zoom Selected. And so now we can get a closer view of what that warning is giving us. And if we zoom in closer here, we can see that we have two nodes here. And we want to fix this. And so you can see this node here is connecting these two members, and this node here is connecting these four members. And so we can see that this member here is just a little off axis. If we go down here, and you can see that this member wasn't connected properly, so the program added in a rigid link here. And again, you can see we have two nodes there. And so this is a simple fix. What we can do is simply merge these nodes. And so I can hold Control and click on both of those nodes, and I can right click on them and hit Merge Selected Nodes. And now you can see down here in the bottom left, it's telling me to pick a target node, and this is our target node. So I'll select that, and you can see that now that analytical member has been moved as the node has been merged, and so now we only have one node there. And again, down here you can see that rigid link has disappeared as our node has been merged. And an important note on this is that this only affects the analytical member and not the physical. So only the analytical member will move. The physical model will not be affected by this. And so then if we go back under the Analysis and Design panel and see, if we go under Display Warnings, that our second warning there has disappeared, which is good. So that tells us that all of our model is connected. And so now that And so now the last thing I want to show you before exporting this model into Rfem is I just want to point out that you can change the position of the analytical member within the physical, or you can change the axial position. And so if I double click on one of these, we can go to, for this column for example, we can go to position. And under position, we can change this from the reference axes to the top center if we'd like. So you can see how the axis has moved there to the top center of the member. And so that is one bit of information I wanted to point out on how you can change the position of the analytical member. So now let's transfer our analytical member into Rfem. So if I exit out of the analysis and design panel, we can take a look at the materials that I have set for each member. So you can see that I have the correct profile and the correct materials set for each member. And this is mapped out again in my conversion tables here. So I have my W shapes here entered as a regular expression. And so all of my W shapes are converted. And then I have my steel A992 material here set for the export and mapped out correctly as well. And so now we can transfer this model, so we can go up here to export and export to Rfem, and we can override this bad physical model that we have right now. So if I go up here to export to Rfem and I choose analytical model, we can click OK. And so that connection is being made. Again, you can see the status there. And now we have our analytical model. Rfem. So if we zoom in here, we can see everything is connected properly. And we can also change the rendering. And so now we can see that if I change my rendering down here to be based on the section, we can see that the correct sections have been imported in, my correct W shapes, along with the correct material and the correct member type as well. So these member types are set to truss, which means they have pinned start and end conditions, so moment transfer will not be there, it's released. We have our correct supports down here. We have our hinge supports and also our roller supports here. So I can double click on one of those. Take a look at that. And so now we want to define our X bracing. And so to do this, we can go up here to create a new single member. I want this member type to be set to tension. So with this member type, it's nonlinear, which means that this member can only take tension forces and not compression forces. And then under the section tab here is where I can define my section and material. So I'll open the section library and I will go to my standardized steel bars. I filter to the ASC and we want to choose our 3/4 of an inch diameter bar. Then we want to give this the correct material. So under steel, ASC 360/22, we want to choose the Steel Imperial A336 material. now that we have our material and section defined, we can click OK. And now we can draw and snap to the nodes here to create our brace members, making sure to snap to our nodes so everything is fully connected, like so. We're going to do the same thing for the back side. So now our X bracing is defined. You can see that here. And we can move on to adding our loading in. And so before we add the loading, we have to create load cases for the loading to be assigned to. And if I go up here to my base data, under add-ons, you can see the combination wizard and classification has been set. So the so our standard here, the AC7, we can have our action categories set based on that, and then our load combinations created automatically. We have our load wizard turned on, so we can create or use the snow or wind load generator, and this is where you can set that standard. So we'll click OK, and we'll go up to this button to create a new load case. And this first load case is going to be self-weight. We want to create a new static analysis setting. This is going to be set to geometrically linear. And then we can create 2 new load cases. This one will be live with an action category of live. And then this one will be snow load. And that will be set to snow. And we'll click apply. And then under the design situations, this is where we want to create a design situation, which is our envelope solution and this is how our load combinations will be created automatically. So we'll set this to our LRFD design situations, and we'll create a new combination wizard. This one will be with a static analysis setting of second order. This combination wizard will create load combinations automatically based on the AAC7, and you can see here those combination rules from the standard with the factors and everything, so you can get a good look at that. Under the load combinations, you can see here those are again generated automatically based on that design situation. You can see those that overview here, and now we can click OK. Now we have our load cases that we can assign our loading to. We'll start off with live load. We're going to keep self-weight. We're not going to change self-weight at all. We're just going to have that be self-weight, which is generated automatically. And for our live load, we want to use one of our load generators. So if we go up here to insert, and go into load wizards, we have a load generator called member loads from area load wizard. So we can create member loads via an area load. And so here we have live load set to uniform and the global Z direction. And now we just want to give this a magnitude. And so then under geometry, we want to select the geometry or the corners of this area. So I'm going to add this to this first floor here and select all of my corner nodes using that graphical button. And then we also want to remove influence from members parallel to this straight member here and selecting that graphically and then clicking OK. And so now you can see this area load on that floor over those members, and if you want to display this separately, you can do so like that, and we can decrease the graphical size of this, and so yeah, now you can see the member distribution there. And so I'll uncheck that, Now we want to move on to our snow load. So with this, we're going to use another load generation or wizard tool. And this is our snow load wizard tool here. So I can right click on snow loads and create a new load wizard snow load. And so the roof type is selected here as flat/mono pitch. And then we want to give this a name. So we'll name it roof 1. And we'll choose this graphically again. Going around here and selecting our corners. Then under the next tab, parameters, we can either enter these parameters as user defined, or we can enter them as map using the map and parameters. And with this, we can enter this information in automatically from our GeoZone online GeoZone tool by clicking that button that was down there. And so it's set to snow, and then you can enter any address in that you would like. I'm going to type in Philadelphia, PA, which is the location of our US office. And then you can see here, you'll get your ground snow load, and you can click OK. And then all of that information will be filled out automatically under our parameters here. And we will get our loading results. And so then we can make a copy of that first load. We'll name the second one roof 2, third one roof 3, and then all we really need to do for these copies is change the location of our snow load here. So we'll change the geometry like so, and then we'll change roof 3 here to this sloped portion. Now that we have those, we can click OK, and we can see our snow loading there. So if I right click and display separately, you can see how that loading is distributed. And you can remove influence from any of these members if you'd like. But that is the loading we have now. So we have our live load and snow load, and then the dead load with the self weight of the structure. And now we want to run our steel design. So first I want to go up here to the base data and go under add-ons, and I want to check on steel design and click OK. So we're turning our steel design add-on on, which gives us our folder down here. And so I'd just like to say that this webinar is not focused on design. And so to save time, I'm going to disable the stability analysis. And so to do that, I can right click on my strength configuration settings here and go to edit and turn off perform stability design and click OK. And if you want more details on the steel design, there are dedicated webinars for the ASC and CSA steel design on our website that are recorded, that if you'd like to get more into the details of that, you can check those out. And so now we can run the steel design by going down here into our tables and going to steel design. You can see for our input data, we have our design situation. So we're just looking at our strength limit state. For steel design, the objects to design, we're designing all of them. Materials here we have entered, and then our sections. And so what we can do is go up here. Okay, so I need to make a correction. This roof, or this snow load, roof 1 here, needs to be defined at the top here. So we'll go in there, double click it, and fix it. And we will click OK. And so now let's run our steel design by clicking the button here, show results. So the steel design will run. And now we can see our design ratios. We can get an overview of the ones that are not passing or red and above the 1.0 design check. And so I can show you how to optimize these now. we can even get a better view if I turn off the loading here. I can select these members and I can isolate them, and we can see here that we change the rendering. You can see here that our 8x13s are not passing here along with our 10x17s. We can even go down here, design ratios on members, and we can take a look at that. So we can even check, get our design detail checks. And we can also look at these design ratios by section. So again, our 8x13, our 10x17. So we can go to the input data, go under sections here, and then we can go to our 8x13 here and choose to optimize this current row. And we can go under 10x17 and choose that option again. And so with this option, the program will choose the smallest section possible to get right below that 1.0 design ratio. And so we can go up here and click on Calculate All to rerun the calculation. And you'll see that that optimization is being run for the steel design. And so now all of our ratios are below 1.0. You can see this one's at 0.19 or 0.91. And if any of these ratios are too high for you, getting too close to 1.0, under the input data, we can go in here to the global add-on settings, and you can adjust that factor. So for the optimization to any factor you'd like. And so now that these sections have been optimized, we want to right-click on them. We want to right-click on them, and we want to choose this option to use all optimized sections in model. We want to click yes. It's going to delete the results because we're going to have to rerun the results based on the new self-weight. And so now we have our steel design. And so now to summarize, what we did was we imported our model in from Tekla, and we added some bracing and loading. And then we ran the steel design. And so now what we want to do after optimizing the sections that were failing, we want to update our structure in Tekla with our new additions and cross sections as well. So we can go back to Tekla here. And in Tekla, what we want to do is choose the import from Rfem. And that connection will be made between the two programs. And so now what we want to do is choose the update existing model here. We also want to, of course, import in the analytical parts, and choosing update existing model, we can use these options down here to choose what we want to update. So we want to update materials, cross sections, thicknesses, and also add in some new objects and remove non-existing ones. So we'll click OK. And now you can see that in Tekla, our bracing has been added with the correct profile and material, and then the correct sections here have been updated as well. So we have our 12x14s here with our correct material. And so yeah, that's the workflow. So what we've done was we've gone from Tekla with the model that was created here. We created an analytical model that was then exported to Rfem, where we ran the analysis and design optimized some sections, and then imported this and updated the model in Tekla with the new sections and materials. The last thing is probably the documentation for the steel design is what we want to create. And to do this, we can create our printout report. And so we can go up here to new printout report, and we can go down here to save and show. And so then the printout report will pop up here, and you can see here what it looks like. We have our pages, we have all of our information here laid out. So we have our materials, our sections, and then we have our steel design down here. So we have our objects to design, design situations, materials, and some results of our ratios. We can even get a design overview. And inside this printout report, we can also add in some graphics. You can keep the printout report open in the background while you're still using Rfem. So let's say we want to add this graphic. We can go up here and choose Print Graphics to Printout Report. And so then we have some options here. Maybe we want to check on window filling. And so then we can hit Save and Show. And so then we can see that graphic has been added to our printout report. And if you want to edit this graphic at all, you can right click and hit edit, and you can, frame it differently and change the perspective, and also change that sizing. And also you can change the rendering, or you can show loading and change a lot of different things there. Next, if we want to show some of our steel design results, we can do that. So we can turn on our steel design results so we can show those graphically here. And then we can also print this graphic to our printout report. So we'll hit Save and Show again. And then that graphic is added to the bottom here under our steel design. And if you want to also add in the steel design detail checks, you can do that as well. So if you want one of these detail checks shown in the report with the equations and everything and references to the AAC standard, we can go down here to Print Graphics to Printout Report. And then we can again open our printout report, and we can see that information has been added here. Yeah, and so then you can take this report and you can export it as a PDF if you'd like and share it. Also, I would like to note in the report, you can change what is shown in the report here by going up to this button, and you can edit what is being shown in the report, and you can also save templates as well, and you can move information around along the printout report navigator on the left hand side here. So that is all I wanted to show regarding the Tekla integration with Rfem. I wanted to end on some future developments that we're going to add into this integration. I want to start off by saying these are the planned future developments, of course, and they are in order of planned release dates, and listed from the soonest release date to some more distant dates. So the first information, or The first thing we're going to add to this integration is member sets. So these will be transferred between Tekla and Rfem, and this should be available either next week or the week after. Then we want to eventually add the ability to use tapered members in the conversions. Then also the ability to export load groups and loads from Tekla to Rfem. And then in the far distant future, add the ability to consider eccentricities in the integration workflow. And with that said, I will hand it back to Amy to finish off the presentation.
All right, perfect. Thanks, Alex. So this presentation was recorded and will be placed on the same web page that you registered for the GoToWebinar. The model used in the presentation will also be available for download. So we encourage everyone to go ahead and access the free 90-day trial version if you don't already own Rfem, where you can test out this Tekla integration yourself. And if you have any questions about the presentation today or any products, you can contact us in our Philadelphia office with the information shown at the bottom of the page. Our phone number is 267-702-2815, and our email address is info-us@delubal.com. If you are interested in scheduling an online demo, or you'd like to have a more in-depth discussion about Rfem and any of the products that we have available to us, feel free to contact our sales team with the QR code shown here. It takes you directly to our webpage where you can initiate that. And of course, our contact information again is shown at the bottom of the page, where we can go ahead and schedule that online demonstration or presentation within the coming weeks. We will have many more upcoming webinars. These are presented about once a month. You can register at delubal.com under support and learning webinars. As most of you know, we tend to send out a reminder email about a week before these take place, so just keep an eye out for that. PDH certificates will automatically be emailed to all participants who were here for the full presentation. That is a requirement that states that we are pre-approved providers, that you are here for the full 60-minute duration in order to receive that PDH. Now, if you did watch with a colleague or in a conference type setting and you yourself did not register with your own name and your own email with the GoToWebinar, you will need to request that PDH at the email address shown here, info-us@delubal.com. So again, if you yourself did not register, but you were here for the full presentation, go ahead and send us an email requesting that PDH and let us know who you watched it with. Now, the PDH is not instantaneous. As soon as this webinar ends, it's typically sent out in the next 1 to 2 days through that email that you registered. And with that said, we want to thank everyone. And as always, we hope to see you at the next presentation. Thank you.